This is a question from JEE Advanced 2019. Let alpha and beta be the roots of x squared minus x minus 1 is equal to 0 with alpha greater than beta. For all positive integers n, define an is equal to its alpha raised to n minus beta raised to n by alpha minus beta, n greater than or equal to 1, b1 is equal to 1, bn is equal to an minus 1 plus an plus 1 for all n greater than or equal to 2, then which of the following options is bar are correct? So before diving deep into the question, there is a quadratic given in the question, x squared minus x minus 1 is equal to 0. Let me spend some time discussing about some of the interesting properties of this quadratic. So just like we have this quadratic x square plus x plus 1 is equal to 0, whose roots are omega and omega square, and omega and omega square comes with a lot of interesting properties. And similarly, this quadratic has roots given as alpha and beta. When you evaluate, these numbers are 1 plus root 5 divided by 2 and 1 minus root 5 by 2. Okay, and this number is usually called the golden ratio, and this is nothing but, and golden ratio is usually represented as the Greek letter phi, and this is usually represented as psi, which is nothing but the conjugate of the golden ratio. This number is approximately 1.618 in decimal form, and this number is approximately 0.618 in decimal form. Okay. So let's look at some of the interesting properties of golden ratio. First of all, golden ratio is nothing but a root of the quadratic x squared minus x minus 1 is equal to 0, and that number is given by phi is equal to 1 plus root 5 by 2, and its value in decimal form is 1.618. Secondly, the square of golden ratio, phi square, is nothing but phi plus 1. You know why this is true? Because it satisfies x square is equal to x plus 1. So phi square is equal to phi plus 1. And third property is, phi square is phi plus 1. So if you divide it with phi, we have phi is equal to 1 plus 1 by phi. So from this we have phi inverse is equal to phi minus 1. So this is one interesting property. Phi square is equal to phi plus 1. Phi inverse is equal to phi minus 1. This question is directly linked to golden ratio. So that is why I am trying to give you all these details about golden ratio. This is strictly not in the JEE syllabus, but these are interesting properties to note. So these can be used in some other exams like Olympiad or ISI or KVPY or something like that. Okay, where non-routine questions may be asked. And the next idea is, because phi squared is equal to phi plus 1, and if you multiply the entire equation with phi power n minus 2, we have the nth power of phi as a sum of n minus 1th power of phi and the n minus 2th power of phi. This is another interesting result. And the other idea is about the geometry of the golden ratio. Okay, suppose there is a line segment PQ which is being divided by another point R in the ratio A is to B. Okay, suppose if this ratio is golden ratio, suppose this ratio is given by golden ratio, we know that phi is also equal to 1 plus 1 by phi. Okay, so this is nothing but 1 plus b by a. So this is nothing but b plus a by a, and this b plus a ratio is PQ ratio and A is PR ratio. So what we just got is, if R is dividing the line segment P and Q internally in the ratio RP by RQ. That ratio will also same as PQ by PR ratio. Okay, that is what we just obtained from the geometrical interpretation. So if R divides P and Q internally in the ratio of golden ratio, then P will divide the join of Q and R externally in the ratio of golden ratio. Okay, another geometrical significance is about the golden rectangle. Golden rectangle. So a rectangle whose sides are in the ratio of golden ratio. So A, B, and if A by B ratio is 5, the interesting property is if you go and place a square adjacent to it, thus creating another rectangle. Now the ratio of sides of the new rectangle formed will be A plus B by A. So since A by B is 5, this is nothing but 1 plus 1 by 5. This is again 5. So the interesting property is that you take a golden rectangle. A golden rectangle is a rectangle whose sides are in the ratio of golden ratio, and then you place a square adjacent to it and thus forming another rectangle. Now the new rectangle formed will also be another golden rectangle, and you can keep doing this process again repeatedly. That is another significance. Now another interesting property is phi can be represented as root over 1 plus phi, because phi square is 1 plus phi. So phi is root over 1 plus phi. So we can write this expression as 1 plus root over 1 plus root over 1 plus so on and so. Another interesting result is, since phi is equal to 1 plus 1 by phi, we can write this as phi is equal to 1 plus 1 by 1 plus 1 by 1 plus 1 by and so on. Right? Another interesting relationship is in trigonometry. You know, cos 36 degrees is root 5 plus 1 by 4. So our golden ratio is nothing but 2 cos 36 degrees, which is nothing but 2 cos of 360 is 2 pi by 10. So that is pi by 5, 2 cos pi by 5. And most importantly, I hope you have heard about the Fibonacci sequence. If you take the terms of Fibonacci sequence 1, 1, 2, 3, 5, 8, 11 and so on. If you take the ratio of consecutive terms, you will observe that as the sequence as sequence progresses, the ratio between consecutive terms tends to the golden ratio. Okay. In other words, if an is the general term of the sequence, the limiting value of an by an minus 1, or you can say an plus 1 by an ratio, will be phi. Okay. And this is very easy to prove, because if you call this L as the limiting value of the ratio of consecutive terms of the sequence an plus 1 by an, this can be written as limit n tend to infinity an plus 1 can be represented as an plus an minus 1. Why? Because Fibonacci sequence satisfies this recurrence relationship, an plus 1 is equal to an plus an minus 1, right? So this is going to be 1 plus limit n tend to infinity an minus 1 by an. Now this is nothing but the reciprocal of the value of the limit we are looking for. This is 1 plus 1 by L. So L is equal to 1 plus 1 by L, and if you solve the quadratic, you are going to get L as phi. Right? That is one of the most remarkable properties of golden ratio. That is, you take the terms of Fibonacci sequence, and as the sequence progresses, the ratio between consecutive terms keep getting closer and closer to the golden ratio, and in the limiting case, this ratio will be nothing but the golden ratio. That is another important property. Now, coming to this question, in the question, see, there are two places where a linear combination of alpha raised to n and beta raised to n are taken. Okay, here you are forming a sequence by taking a linear combination of alpha power n and beta power n. Also, in one of the options, there is another sequence which is given as a linear combination of alpha power n and beta power n. Now, let's look at what is the relevance of this linear combination of alpha power n and beta power n. So, this alpha and beta are not just two random numbers. So, they are nothing but the roots of the quadratic x squared is equal to x plus 1, and one of the numbers is golden ratio and the other number is its conjugate. Okay, so these are not just random numbers. Not every linear combination of roots of any quadratic will not satisfy what I am going to tell you soon. Okay, so that you should remember. Now, I am going to take a linear combination of k1 alpha power n plus k2 beta power n. Now, if I call this an, alpha and beta are the roots of the quadratic x squared is equal to x plus 1. Let's see some of the important properties of this sequence obtained as a linear combination of alpha power n and beta power n. Of course, a1 is going to be k1 times alpha plus k2 times beta. a2 is going to be k1 alpha square plus k2 beta square, and so on. K1, K2 are some real numbers. Okay, and interestingly, we can see that if you multiply this expression with x power n, we have x power n plus 2 is equal to x power n plus 1 plus x power n, which means both alpha and beta will satisfy these two conditions. Alpha power n plus 2 is going to be alpha power n plus 1 plus alpha power n. Similarly, beta will also satisfy the similar condition. Beta power n plus 2 is going to be beta power n plus 1 plus beta power n. Now, you multiply the first equation with k1, multiply the second equation with k2, and you add these two expressions. What will you get? On the LHS, we have a n plus 2, because on the LHS we have k1 power alpha, k1 into alpha power n plus 2 plus k2 into beta power n plus 2. That is going to be a n plus 2. On the RHS we have a n plus 1 plus a n. So, that is a very important thing. We have just realized that this will satisfy a linear recurrence relationship. So, this sequence generated by taking a linear combination of alpha power n and beta power n will satisfy a recurrence equation. This is called a recurrence equation. Okay, that is one remarkable property. Fine. So, a specific example is when an is taken as 1 by root 5 times alpha power n plus minus 1 by root 5 times beta power n. Okay, so k1 is taken as 1 by root 5, k2 is taken as minus 1 by root 5. So, in this case, a1 is going to be alpha minus beta divided by root 5. Alpha is, so we know that alpha value is root 5 plus 1 by 2. Beta value is 1 minus root 5 by 2. So, we have alpha minus beta as root 5 and alpha plus beta as 1, right? So this A1 quantity is going to be root 5 divided by root 5, that will be 1. And now A2 will be alpha square minus beta square by root 5. So this is alpha minus beta into alpha plus beta by root 5. So that will be again 1. Now you can use the recurrence relation to find the next term onwards. A3 is equal to A1 plus A2, that is going to be 2. A4 is equal to A3 plus A2, that will be 3. Similarly, A5 is equal to A3 plus A4, that will be 5, and so on. So let's summarize what we just learned now. So you take a linear combination an as a linear combination of alpha power n and beta power n. One very special case, and in this case the sequence is going to generate the Fibonacci sequence, right? So that is one very important property, one important special case of this recurrence relationship formed by a linear combination of nth powers of the roots of the quadratic given in the question. Okay. This Fibonacci sequence has lot of significance in design and nature. So I suggest you to look it up on the web. Now let's move on to our question. So in our question, so you can observe that in an is nothing but alpha power n minus beta power n by alpha minus beta. So it should strike you that it is nothing but the Fibonacci sequence given in the question, because alpha minus beta is root 5. So this an is nothing but, in this case an is nothing but 1 by root 5 alpha power n plus minus 1 by root 5 beta power n. So an is nothing but the Fibonacci sequence, right? Now there is one more sequence in the question, bn, given as b1 is equal to 1 and bn is equal to an minus 1 plus an plus 1. So now let's see what that sequence bn is. So b1 is equal to 1, your b2 is going to be a2 plus a3, a2 plus a3 will be 1 plus 2, which will be 3. B3 is going to be a2 plus a4, that will be 1 plus 3, that will be 4. B4 will be a3 plus a5, a3 plus a5 will be 2 plus 5, that will be 7, and so on. So Bn sequence follows this pattern, that is 1, 3, 4, 7, and so on. Again, you can observe that this sequence also follows a recurrence relationship. See, you can see that b1 is equal to 1, and b2 is equal to 3, and bn plus 2 is nothing but bn plus bn plus 1. So there is a hint that Bn can also be written as a linear combination of alpha power n plus beta power n. And obviously, when you look at the option B, it talks about a linear combination of alpha power n plus beta power n. So we need to verify that whether it is true or not. Okay. So let's try to do it. So we will assume that Bn is of the form k1 power alpha, k1 into alpha power n plus k2 times beta power n. Now we will prove that k1 and k2 are both 1. So we know that when n is equal to 1, it is 1. 1 is equal to k1 alpha plus k2 beta. And when n is equal to 3, it is When n is equal to 2, it is 3. So this is k1 alpha square plus k2 beta. Now both alpha and beta satisfy this condition that alpha square is equal to alpha plus 1 and beta square is equal to beta plus 1. So this is going to be k1 alpha plus 1 plus k2 beta plus 1. So this is k1 alpha plus k2 beta plus k1 plus k2, and that is 3, and this is 1. So we have k1 plus k2 is equal to 2, and now k1 alpha plus k2 beta is nothing but we can substitute the values. So k1 into 1 plus root 5 by 2 plus k2 into 1 minus root 5 by 2 is equal to 1. So this is k1 plus k2 divided by 2 plus root 5 by 2 into k1 minus k2. Now k1 plus k2 by 2 is 1. So this 1 gets cancelled. So we have k1 is equal to k2. We have this has to be 0. So we have k1 equal to k2 and k1 plus k2 is 2. So both k1 and k2 are nothing but 1. So our b1, bn will satisfy what? Alpha power n plus beta power n. So we have proved that part of the question. So this statement is true. Okay. So we had a gut feeling that that was true because it was given as a linear combination of alpha power n and beta power n. We just had to verify that the coefficients were 1 and 1. So we just verified it. You can also do it using the actual definition of Bn given from the question. So in this case, what did we do? We just wrote down few terms of Bn and realized that this follows a recurrence relationship. From that we understood that Bn has to be a linear combination of k alpha power n and beta power n. From that we gave initial values and found out the values of k1 and k2. Another way is, so Bn is given as alpha n minus 1, sorry, an minus 1 plus an plus 1. So this is going to be alpha power n minus 1 minus beta power n minus 1 by alpha minus beta plus alpha power n plus 1 plus beta power n plus 1 by alpha minus beta. Right. Now we can simplify this expression. Take alpha power n minus 1 out, that will be alpha power n minus 1 into 1 plus alpha square minus beta power n minus 1 into 1 plus, so this will be negative 1 plus beta square whole divided by alpha minus beta. Now 1 plus alpha square is 1 plus alpha, so this is alpha power n minus 1 into 1 plus alpha minus beta power n minus 1 into 1 plus beta whole divided by alpha minus beta. So this will be alpha power n minus 1, substitute for alpha, so it will be 2 plus 1 plus root 5 by 2, and this is minus beta power n minus 1 into 2 plus 1 minus root 5 by 2 whole divided by alpha minus beta. So upon simplification, this will be alpha power n minus 1 into 5 plus root 5 by 2 minus beta power n minus 1 into 5 minus root 5 by 2 by alpha minus beta. And this alpha minus beta is nothing but root 5. So you can cancel it off everywhere. So this will be alpha power n minus 1 into root 5 plus 1 by 2 minus beta power n minus 1 into root 5 minus 1 by 2. So this is going to be alpha power n minus 1 into alpha minus beta power n minus 1 into minus beta. So this is alpha power n plus beta power n. That is another way of proving it. So we have that answer ready. So we have this answer ready. Okay. Now again in question number C, in option C, we have to find the sum of n terms of the sequence an. So let's try to get a general answer for that. get the general answer for that. Suppose if any sequence an is given as k1 alpha power n plus k2 beta power n, we know that this will satisfy a recurrence relation an plus 2 is equal to an plus 1. This is what we know, right? Now our aim is to find the sum a1 plus a2 up to an, that is sigma k is equal to 1 to n ak. This is what we need to find. So the trick is you write a1 as a3 minus a2, a2 as a4 minus a3, and a3 as a5 minus a4, and similarly an will be an plus 2 minus an plus 1, and an minus 1 will be an plus 1 minus an. Add everything, we can see that on RHS terms will keep getting cancelled. A3 gets cancelled, A4 gets cancelled, A5 here will get cancelled. Similarly an plus 1 will get cancelled, an will get cancelled. So on the LHS we have sigma ak, k is equal to 1 to n, and on the RHS it is nothing but an plus 2 minus a2. So this is another important result. The sum of the first n terms of the recurrence relationship is an plus 2 minus a2. It is an plus 2 minus a2. an plus 2 minus a2 is the answer. an plus 2 minus a2 is the answer. So that is one way of proving it. Okay, that is one way of proving it. You can also prove it from the definition we have used, that is ak is k1 alpha power k plus k2 beta power k. So sigma k is equal to 1 to n is sigma k is equal to 1 to n. Now this is k1 times sigma k is equal to 1 to n alpha power k plus k2 times sigma k is equal to 1 to n beta power k. So this is k1 into, this is a GP, first term into common ratio raised to number of terms minus 1 by common ratio minus 1 plus k2 into beta into common ratio raised to number of terms minus 1 by common ratio minus 1. So this can be simplified as k1 into alpha into beta minus 1 into alpha power n minus 1 plus k2 into beta into alpha minus 1 into beta power n minus 1 divided by alpha minus 1 into beta minus 1. Okay, now this is k1 into alpha beta is 1, so alpha beta is minus 1, so it is minus 1 minus alpha into alpha power n minus 1 plus k2 into beta alpha is minus 1 minus beta is this expression into beta power n minus 1 by, and in the denominator we have alpha beta minus beta plus 1, and now alpha beta is minus 1, so it gets cancelled with 1, and minus alpha minus beta is minus of alpha plus beta, which will be minus of 1. So this entire expression in the denominator is minus 1. So let's cancel 1 minus 1 from the numerator. So this will be k1 into 1 plus alpha into alpha power n minus 1 plus k2 into 1 plus beta into beta power n minus 1. So when you simplify it, we have k1 into alpha power n plus 1 plus alpha power n minus alpha square plus k2 into beta power n plus 1 plus beta power n minus beta square. Why? Because we have minus 1 term here, minus alpha term here, so I have rewritten as minus alpha square. Similarly, 1 plus beta term I have rewritten as beta square. So 1 plus beta into minus 1 term I have written as beta square. Or we can directly say write this expression in this way. we can directly write this as k1 into alpha square into alpha power n minus 1 plus k2 into beta square into beta power n minus 1. So this is going to be k1 into alpha power n plus 2 minus alpha square plus k2 into beta raised to n plus 2 minus beta square, and this is nothing but an plus 2 minus a2, an plus 2 minus a2. So that is another way of doing it. Okay, you can also do it using mathematical induction. Okay, and one more way to do this is, so our Sn is a1 plus a2 plus a3 plus up to an minus 1 plus an. So what I am going to do is, I am going to artificially introduce one a2 here. Okay, so you have to add a2 on both sides. Now this a2 plus a1 will give me a3. Now this a3 plus a2 will give me a4. Now this a4 plus a3 will give me a5. Okay, and similarly if you keep doing that, ultimately the answer is going to be an plus 2. So our Sn is nothing but an plus 2 minus a2. So in this case a2 was 1 because it's a Fibonacci sequence. So our Sn is an plus 2 minus 1. Our Sn is an plus 2 minus 1. An plus 2 minus 1. So that answer is also right. Okay. Now we have two options A and D. Both of them look very similar question. We have to evaluate sum to infinite terms of a sequence. So we have a hint that it might be a GP. So let's try to do it. So we have sum to infinite terms of Bn by 10 power n and sum to infinite terms of An by 10 power n. So sum to infinite terms of An by 10 power n. Okay. So this An is nothing but alpha power n minus beta power n by alpha minus beta into 10 power n sigma n is equal to 1 to infinity. So you take 1 by alpha minus beta out, we have sigma n is equal to 1 to infinity alpha by 10 whole power n minus sigma n is equal to 1 to infinity beta by 10 whole power n. Now both alpha by 10 and beta by 10 are proper fractions, so you can apply the formula for sum to infinite terms of a GP. So this will be 1 by alpha minus beta into alpha by 10 by 1 minus alpha by 10 minus beta by 10 divided by 1 minus beta by 10. So when you simplify this expression, this will be 1 by alpha minus beta into alpha divided by 10 minus alpha minus beta divided by 10 minus beta. So simplify this expression, this will be 1 by alpha minus beta into 10 alpha minus alpha beta minus 10 beta plus alpha beta divided by 100 minus 10 into alpha plus beta plus alpha beta. So alpha beta gets cancelled. In the numerator we have 10 times alpha minus beta gets cancelled with the denominator. So we have 10 divided by 100 minus 10 minus 1, which is 10 divided by 89. So that answer is 10 divided by 89. Now let's check that option. So this answer is correct. Now the next option is option A. We have to evaluate sigma n is equal to 1 to infinity Bn by 10 power n. Bn by 10 power n. Sigma n is equal to 1 to infinity Bn by 10 power n is going to be sigma n is equal to 1 to infinity. Bn is alpha power n plus beta power n by 10 power n. So this is sigma n is equal to 1 to infinity alpha by 10 whole power n plus beta by 10 whole power n. Again we have sum to infinite terms of 2 GPs. So this is going to be alpha by 10 divided by 1 minus alpha by 10 plus beta by 10 divided by 1 minus beta by 10. So this will be alpha by 10 minus alpha plus beta by 10 minus beta. So when we simplify this expression, this will be alpha into 10 minus beta plus beta into 10 minus alpha whole divided by 10 minus alpha into 10 minus beta. So this will be 10 alpha minus alpha beta plus 10 beta minus alpha beta divided by 100 minus of 10 times alpha plus beta plus alpha beta. So 10 times alpha plus beta is 10 minus alpha beta minus alpha beta. So that is going to be 2 plus 2 by 100 minus 10 times alpha plus beta is going to be 10 minus 1. So that is 12 divided by 89. But the given answer is 8 by 89. That is wrong. Okay. But if you make a small mistake here, see, alpha beta value is minus 1. Instead of minus 1, if you put 1, this you will put as minus 1, this you will put as minus 1. The numerator will be 10 minus 2, 8 by 89 you will get, which is wrong. Okay. So you should be very careful, because the options will be designed in such a way that even if you make a very silly mistake, you will end up getting the wrong answer and one of the answers, one of the options given, right? Okay then, so B, C, D are the right answers. Okay then,